Hello everyone, welcome to my presentation on Boa Views. Boa Views enable modularization and sharing of Boa queries. This was work done by my previous master student, Shian, and just note that although this work was done at Bowling Green, I'm currently with University of Nebraska-Lincoln. So real quick review here, what is Boa for those of you that may not know? So Boa was originally published in ICSI 2013, and since that time we've added quite a few extensions to it, essentially things like support for abstract syntax trees, support for program analysis on top of those syntax trees. But really at the end of the day, Boa is a programming language and supporting runtime for that language. And so here we can see an example query. This example query is trying to compute all of the fixing file counts. So what it will do is essentially go over all of the input GitHub projects in the Boa dataset, and for each unique project and each unique file within that project, it will figure out how many times was that file changed inside a fixing revision. And this makes use of a special function called isFixingRevision, which essentially just looks at the commit log to determine whether or not that particular revision was a fixing revision or not. So you can see there are different pieces to the language, things like types, and there's a lot of built-in primitive types, there's compound types, there's what we call aggregators. So the line 2 fixing file count is an output variable, and it makes use of the sum aggregator. So it's going to sum all the values, in this case the value is always the value 1, and it will figure out the total sum per project and per file. And then what you do is you take your query and you submit it to the Boa website. You select one of the data sets, so in this case it might be September 2015, and there are small, medium, large, so that you can test on smaller samples before you run it on the full data set. And then once you submit that query, you actually get what we call a job, and jobs all have unique numbers. The job just shows the input query, the data set that was being queried, and the status of that particular query. And if the execution finished without any kind of error, you can also view or download the job's outputs. On the back end, the infrastructure actually makes use of the MapReduce runtime. So it runs on Hadoop, and you don't really need to know a whole lot about MapReduce, but it is important, especially for this particular talk, to understand that it is doing MapReduce on the back end. But at the end, what you wind up with, if the query works, is output that looks something like this. So it's in a tabular text format where you'll see the name of the output variable. You'll see each of the indices. In this case, the first index is the project ID, the second index is the path of the file, and then you'll see there's an equals. For this query, the equals is just how many times was that particular file changed inside of a fixing revision. So now let's consider a motivating problem. So specifically, the problem we're going to be looking at is how to find all of the buggy files by examining the past bug fixing behavior in the systems. So what we'd like to do is essentially analyze this problem using Boa. And if we do that, then what we need to do is come up with a Boa query that computes the following three things. First is the fixing file counts, and this is per file. This is very similar to the code that I showed previously. Second thing is the fixing revision counts, or the FRC. This is actually going to be computed per project, and it's the total number of fixing revisions in that project. And then we need to know the average fixing revision count across all of the projects. Once we have that, we can then go download that Boa output. We can use something like the Boa API, or if we want to, we can go to the website and just download it from there. The second analysis task, though, is to actually go and filter all of the projects using standardized mining software repositories criteria. Things like having a minimum number of commits, or possibly a minimum number of committers, or a long enough timeline, right, to try to filter out things like toy projects or class projects and things like that. This is often very standardized in the field, so we would like to do that in our analysis as well. So then we go and obviously download those results as well. Now that we have these two analyses downloaded, we can go and create the final task, which actually generates the list of all potentially buggy files. What this will do is use both the filtered projects list from the second task and all of the data from the first task to finally generate the result that we want. And then this result can be downloaded and used in our research. Now, a couple things to note about this process. If we think about the task 2A, for example, this is something that ideally somebody else has already created, so that way that I'm using the exact same filtering criteria as somebody else. That way we get kind of the same filtering criteria across lots of different research. But that's a little hard to do within Boa. The other thing to note is that the output from task 1A generates an average across all the projects. We need to use that average in task 3A to filter out the projects where their specific fixing revision count is below that average, because we're only maybe interested in things that are within some point of that average. So this actually points out that Boa does not provide easy reuse of other queries, especially other people's queries, and thus because of that it actually fails to be an end-to-end analysis tool. So our proposed solution is to use the notion of materialized views. Materialized views comes from the database world. And so what do views do? Well, essentially what it does is it allows a Boa query to provide output reuse. So one Boa query can now consume the output of a prior Boa query. And because of that, now you can chain these queries together and therefore get much more complex analyses out of them. We also allow enabling subqueries. So within a single BOA query, you can actually now have subqueries that execute individually. And the runtime system simply manages how these all operate and run, and then we provide a caching mechanism to make sure that everything is efficient. And at the end of the day, what this enables is end-to-end analyses. Now we can do the entire query within the BOA infrastructure. So at a high level, what we're getting is the ability to have a directed acyclic graph of BOA queries. So we can have one BOA query consume the output of one or more previous BOA queries. So if we go back to our example, we can actually have 3 different BOA queries. BOA query 1 is going to generate 3 outputs. BOA query 2 is actually going to consume 2 of those outputs, the FRC and the average FRC, and it's going to use those 2 to do some filtering. And then it's going to have its own output. Query 3 is actually going to consume the output from BOA query 1 and BOA query 2. So now we actually have 3 separate queries. These can be written as literally three separate queries, 3 different jobs, or they can be written together as subqueries within one giant query. But that allows people to decide exactly how they want to handle the modularization within their system and how they want to allow other people to reuse their code or not. So now let's take a look at the view syntax that we provide. So here we've got the example on the left that we've been running with. So there are 3 different queries. On the right, we have the entire code. So even though there's 3 queries, what we were doing here on the right is we're representing them using a single query with what we call subqueries. So when you take a look at the very top at line 1, you see that we state that there's a view. That view's name is fixing revision. And then everything from the opening curly brace down to the closing curly brace on line 18 represents that particular view. Now within that view, we have a standard BOA query. So we have things like output variables. In this case, we're outputting 3 different outputs. And we have some visitor code. And then here we're actually sending the data to the output. So on line 19 to 34, we define another view, or subview in this case, named filter. And then the main part of the query in green at the bottom makes use of those 2 subqueries above. So it makes use of the filter query, specifically the output variable named retained, and it makes use of the fixing revision queries, and specifically the output variable named fixed file count. Now if you notice, the second subview actually does make use of the first one as well. So it references the fixing revision average FRC and the fixing revision fixed revision count. So what this does is it allows people to structure their queries and modularize them in any way that makes sense. You can also nest the queries. So we can take that exact same example as before, but this time take the view fixing revision, and we can nest it inside of the filter view. This won't actually change our output, it just changes the way we reference things. So now at the main portion in green, we're going to say we want the filter view, the fixing revision subview, and then the fixed file count output variable. So what we have is the ability to define views, which are essentially queries, as well as a way to reference views. Now when we talk about referencing views, we always need a query root, and that can be one of 2 things. It can be the capital letter J and then the job ID number, such as 12345, or it can be @ and then the BOA username / and then a tag name provided by that user. So what that does is it allows people to share their code and give it a meaningful name so that people can reference it a lot easier than referencing it by some random job ID. Once you have the query root, then you provide essentially what views or subviews you're accessing, and then you provide what particular output variable name you're trying to get a hold of. So with the previous example, we were essentially referencing what we call internal tables. Here we are making use of what's called the relative view path. We don't need the absolute root. We don't need to say a job number because it's the same job number. So here we just have relative view paths and then the name of the output variable. Now if you are actually trying to reference another job and possibly another user's job, then you do need to make use of the full path. Right? So here we would have to reference it either by J or by @ or Dyer / fixing revision, one of the 2. Once you have tables, you can also do filtering on those tables. So here we have V1, which is a table with 4 columns to it. I've given the name C1, C2, C3, C4 to each column. You can name the columns anything you want. The names don't have to match the original names of the output variable, so it allows you to actually kind of custom tailor it to your particular query. So in this example, C1, C2 are strings, C3, C4 are ints. So when we look at V2, what we've done is we've gone and we've done some filtering. So we've actually filtered out 2 columns. We filtered out the first column with the underscore and the second column with the string foo. And so what that does is it leaves a table with 2 columns, C3, C4, where some of the rows actually are filtered out. And so when we look at this example, we did say foo, so we're only keeping things where it matches foo. Therefore, the second row was filtered out. And if we take that particular table V2, we can filter it even further. So now we can filter it based on the value 3. So as we go down to column C3, if it doesn't match that particular value 3, that gets filtered out as well. Right? And so what happens is V3 is actually making use of the filters that were applied in V2 as well. Now, the underscore is essentially a wildcard. It just says, essentially, I want to drop that column. I don't care about it. So we're not really filtering in that sense. We're just simply making the table a little bit smaller. We're creating what we call a subtable at that point. Now, the other thing you can do with tables is traverse them. So obviously, once we have the table we're interested in, we have to get data out of it. And so the way we do that is first create a table variable. So on line 18, we have the table variable v. We're assigning it to some external table, our Dyer fixing revision, fixed file count. And we're specifically saying that this table should be, a sum indexed by a string of integer values. And so on line 19, we then declare our iterator. This is a row variable. Now the type of this is actually going to be based on the particular table that you're iterating over. So this would be a row where we're expecting essentially a column that's a string followed by a column that's an int. It can be a little cumbersome to write all that out, so we can literally just say v._row and it will figure out what that particular type is for you. So that becomes the type of our particular iterator. We can then go read one row, so we can say v greater than r, and so what we're doing is saying take the table v, read one row, store it into the variable r. And so if we do a while loop over that, then eventually this will return false, and that means we've hit the end of the table. So this is the way you can actually traverse the entire table. Now, once you get a particular row, you can then access subfields or columns from that, and you can do that based on their name, if there is one, or you can do it positionally, such as ._1, 2, 3, and so on. So in this particular example, we actually gave column 1 the name file, so we can actually reference it as ._1 or .file. Now, there's a lot of implementation details, but for the particular shortness of this talk, I'm just going to skip over them, so if you're interested at all, please definitely go take a look in the paper. To evaluate this work, we actually performed two fairly large-scale case studies. So both of them made use of our small cluster, so 15 compute nodes plus one master node. The runtime actually runs on an older version of Hadoop 1.21, as well as Uzi, which is a coordination slash scheduling framework. And so the first case study we did was actually looking at how to split identifiers. So Binkley actually took a look at creating a gold set, and this gold set contained over 2,000 identifiers, and the split form based on over 8,000 human judgments. And later, Hill actually performed an empirical study using identifier splitting algorithms on that gold set. And so what we did was we actually used the greedy splitting algorithm to split all the identifiers found from the gold set, and we also ran the algorithm on Boa's data set as well. So splitting here would be things like taking word 10 and getting word in 10, or hard, capital W word, getting hard and word, and so on. So what we came up with was a set of different Boa queries that actually, it just basically hard-coded the gold set, so we just threw the entire gold set into a Boa query, so it was available. We had another one that just had a downloaded word list from the internet. We had one that had abbreviations, another one with stop words. So the top four are essentially just kind of like predefined data sets that we could make available for anybody to use. And then we had our greedy splitting algorithm that took those as input and actually processed them based and generated the accuracy based on the gold sets. So the results are pretty good. Essentially, our dictionary was kind of similar in size to the previous results, small and medium. It's kind of in the middle, and we got 53% accuracy, which again is kind of in the middle of where they were as well. We didn't really have any way of generating accuracy based on the Boa input data, but based on just an examination of the output, it looked really fairly good to us. So the second case study we took a look at was by Foucault, and what they did was they analyzed 5 open source projects and looked at developer turnover. And so they computed several metrics like internal, external, newcomer versus leaver, and stayers. In our study, we actually analyzed over 1,600 open source projects from the Boa dataset, but we computed the same metrics. So what we wound up doing was generating quite a few Boa queries. Some of them were dealing with just simple things like filtering, but we had one giant query that essentially generated all kinds of different turnover metrics, and then we created different research questions, and we had one Boa query for each of those research questions. And the results were actually a little interesting because some of our results did not match the prior work. And although we're not 100% sure why, we believe that's because the prior work only looked at 5 particular projects, whereas our results were analyzing 1,600 projects. And so we think maybe that the actual overall trends that were being observed match more with what we saw as opposed to what the prior work saw. But we are trying to dig into it a little bit more and just kind of see exactly, why is it different and exactly where those differences are. So in conclusion, Boa Views actually provides the ability for Boa to do end-to-end analysis all within the Boa infrastructure. So now we can actually run queries such as this without having to make use of external tools. Boa Views also enable modularization and sharing of Boa queries, including sharing across users. Our evaluation performed several case studies, including a case study on splitting identifiers, and it did show similar results, as well as a study on developer turnover, which actually showed surprisingly different results. But this particular study is very nice because it shows clearly that BOA is an end-to-end infrastructure. If you have any questions, please let us know.